All right, hi everyone. Welcome back to section 4.6 video. And in this video, we're going to take a look at another non-homogeneous differential equation where we would need to use variation of parameters. So the reason we would need to use variation of parameters is because of this tangent x right here. I know it's just tangent x, but this is actually not a finite product or sum, because you could rewrite this as sine x over cosine x. So it's not a product, it's actually a division. So here is where we would need to use variation of parameters. Okay, so we need to use variation of parameters, but we'll just go ahead and solve this as we normally would for a non-homogeneous differential equation. And that would be identifying the homogeneous part, y double prime plus y, that will give us our complementary. And then the tangent x component is the non-homogeneous part of our differential equation, which gives us the particular solution. So, like we always do, let's go ahead and solve the homogeneous part. So we'll say step one, solve the complementary solution using the auxiliary equation. And that's from section 4.3. Okay, so our homogeneous component is that y double prime plus y equals 0. And the standard form for a constant coefficient homogeneous differential equation is ay double prime plus by prime plus cy equals 0. So when we form our characteristic equation, we have a equals 1, b equals 0, there's no y prime, and c would also equal 1. And so my equation would be m squared plus 1 equals 0. So we go ahead and try and solve the roots for m. So it'll be m squared equals -1. We would square root both sides. And so we can see we're going to get an imaginary number. So this would be plus or minus I. Okay, so remember the form for complex roots, m equals 0, excuse me, m equals alpha plus or minus bi. So just think of there as like a 0 plus or minus I. So that means my alpha is 0 and my beta is just, think about there being an invisible 1 right there. Okay, so these are my alpha and beta. And just remember that the solution to a complex root constant coefficient is y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. Okay, and so our complementary solution here, y sub c, e to the 0x times c1 cosine of just, we could put 1x for now, plus c2 sine of 1x. But then this just ends up being, because e to 0 is just 1, we can drop the 1 inside of the cosine and sine. So c1 cosine of x plus c2 sine of x. Okay, so that's our complementary solution. So that's our complementary. We want to shift focus now to our particular, focusing on our non-homogeneous parts. So for step 2, we want to get the differential equation into standard form. Okay, that just means make sure our second derivative y double prime is naked, so to speak. So our differential equation from up above is y double prime plus y equals tangent x. All right, but the good thing about this is that y double prime is already naked. Okay, so the differential equation is already in standard form. All right, so since it's already in standard form, this tangent x is going to be my input function f of x. Okay, so moving on to step 3 now, that's where we pick our trial particular solution. So make a guess for our particular solution. But as we do with these variation of parameters, it's always u1 times y1 plus u2 times y2. This is always our guess. Okay, don't have to think about anything else. That's always going to be our guess. Okay, so that's our guess. So now what we're going to do is move on to step 4, and that's going to be obtain what u1 and u2 are. So step 4, get u1 and u2. Okay, so just a reminder of the formula that u1 equals negative integral of y2 f of x over the Wronskian of y1, y2 dx. Okay, so we have f of x, we have y2, even though we didn't explicitly state what it was. This is y1, this is y2. We could say note y1 equals cosine x, y2 equals sine x. Okay, and the other thing we need to get is the Wronskian. So let's go ahead and do that. So first, we need to compute the Wronskian. Okay, so the Wronskian of y1 and y2 equals the determinant of y1 and y2. So the cosine and sine. So this would be cosine x, sine x, and this would be negative sine x, its derivative, and cosine x. And so we get the determinant, we cross multiply and subtract. So this would be cosine squared x minus negative sine squared x, which is just cosine squared plus sine squared, and cosine squared plus sine squared just equals 1. So the Wronskian just equals 1. So that's pretty easy to work with. And, just in case this escapes your mind a bit, cosine squared plus sine squared equals 1. Okay, so back to figuring out what u1 is. So u1 equals negative integral of u2, which is sine x times f of x, which is tangent x, all over just 1. Okay, so don't really have to deal with the 1. There's really nothing else to do. I guess what I would like to do to make our integral easier to work with is change tangent x to be sine x over cosine x. And so I need to solve this integral. How would I solve this integral? So there's a couple tricks we can use for this. One thing we can do is combine the signs. So we'd have sine squared x time over cosine x dx. And then what else can I do? Let's see. Um, well, we can use the identity that, sine squared x plus cosine squared x equals 1 that we just used and just isolate sine squared x. So we can substitute in 1 minus cosine squared x. So this would be negative integral 1 minus cosine squared x all over cosine x. And how would I solve this integral? So one thing we can utilize here is separating out the numerator. So what that would look like is negative integral 1 over cosine x minus cosine squared x over cosine x. And so the cosine squared and the cosine could cancel out. And I could rewrite 1 over cosine to be secant x. And so my integral becomes secant x minus cosine x dx. Okay, so we know what the integral of negative cosine would be. Secant x, maybe not the top of your head, but it is something that is proven what the integral of secant x is. And just, I don't want to say recall because it's not something probably the top of your mind, but, the integral of secant x is actually natural log, absolute value of secant x plus tangent x. Okay, so that is an established integral that we can use to our advantage. Okay, you probably solved it first in um, maybe Calc 1 or Calc 2, but here's where we can just use the identity. So this integral turns into negative natural log, absolute value, secant x plus tangent x. And then the integral of negative cosine is going to be negative sine x. Okay, last thing we want to do is distribute in the negative. And so we end up with negative natural log, absolute value, secant x plus tangent x, absolute value, plus sine x. And this is u1. Okay, so I'm betting this was the more difficult integral that we had to deal with. We had some trig tricks that we had to use. So I'm guessing the next one for u2 would be a lot simpler. So let's try that out. U2 equals the integral of y1 times f of x over the Wronskian of y1, y2 dx. So u2 is the integral of y1 was cosine x. So we're using cosine. My input function is tangent x, and my Wronskian is still just 1. So don't have to worry about the 1. I can rewrite tangent as sine over cosine. And look at that, the cosines cancel each other out. And so I just end up with the integral of sine x dx, which is just negative cosine x. So, like I said before, that is our simpler integral to deal with. Okay, so we got u1 and u2. Let's move on to putting this all together into our particular solution. So here we go. Step 5, plug in y1, y2, u1, and u2 into the particular solution. So remember, our guess is always u1, y1 plus u2, y2. And so if we plug in all our components, we get negative natural log absolute value of secant x plus tangent x plus sine x times y1, which is cosine of x, plus negative cosine of x times sine of x. So remember, this is u1, y1, u2, y2. So that's my particular solution. So now let's form our general solution. Step 6, form general solution. And my general solution is my complementary plus my particular. And so my general solution, coming up and grabbing my particular all the way up here, would be C1 cosine x plus C2 sine of x plus, I'm going to write it like this, cosine of x times negative natural log secant x plus tangent x plus sine x minus cosine x sine x. Okay, and that is my general solution. Okay, so another long problem, but make sure you're getting your steps done correctly, taking your time, and dealing with that more difficult integration to help you out with the more simpler integration. But thank you for watching, and I'll see you in the next video. Okay, take care.